Okay, everyone, today is related rates. So as I said last time when we were doing the implicit differentiation, the idea was to practice with that as much as possible so that this section would not be as horrible as it sometimes is. So here we're looking at word problems, and these word problems are going to be a bit of a doozy. So I'm going to write up a little bit of information here first, and then we'll get into a word problem. So this says, we might have a function in two variables as usual, but we may be interested in the rate of change with respect to a third variable. And normally that third variable is time. So we can say normally time. Okay, so no matter what type of word problem we're doing, whether it's a velocity problem or whether it's a profit problem or cost or revenue, or even whether we're looking at like a geometric shape type problem, our functions come to us with two variables, okay, as usual. But sometimes we want to take the derivative, but not with respect. We don't want to know how one variable is changing compared to the other. We want to see how they're both changing compared to a third variable. And that's why normally that third variable is time, almost always, okay? So let's look at an example here. We're going to start with one that is a real world example that we can kind of talk to and through, and hopefully you can visualize, okay? So this one says, oops, that pen is not going to get flustered. It says a pebble is dropped into a pool, forming concentric circles. Yeah, you know what? I'm going to push way too hard on the pen. Let's try another pen here. Sorry about that. We're having rainbow day on the board. Okay, this says, as the radius increases, so does the area of each circle. Find the rate of change. Wait a minute, that is not rate. Try to put two words together at the same time. Find the rate, the area is changing with respect to time. Okay, we're gonna do a pink, I think. Not that pink. Oh, that pink's good. No. Okay. All right. So let's think about this for a second. So you drop a pebble into a pond, and then you start to see this, right? So, or whatever it is you're throwing into the pond, and it sends out little circles. So that's what it's saying. A pebble is dropped into a pool, forming concentric circles. Now, those circles don't stay set, do they? those circles are growing. So as the time passes, the circles are getting bigger and bigger and bigger, bigger and bigger and bigger. And that's what this is saying. As the radius increases, so as the circle gets bigger this way, the area of each circle is also getting bigger, right? So there's definitely a change going on here. But the change, while we're looking at area and radius, the change is happening over time. So you see how we've got radius, area, and then we're bringing in this third time. Now, this says we want the rate the area is changing. So that tells us what function we're interested in. We're interested in the area function. So hopefully we remember that the area of a circle is pi r squared. I know you business people, don't have to deal with this too much, but hopefully you remember that that's the area of a circle. Okay, so we've got our area of a circle, but we want the rate of change. So that means we need to find the derivative. The only issue is we're going to find the derivative with respect to time, which means as we go through this, every time we see a variable, we take the derivative and then we follow it implicitly by the derivative of the inside. So like the derivative of a is just 1, but we're going to immediately follow it with dA dt. Okay, because we're doing this with respect to time, so that means there's going to be a dt on the bottom of each one. Now over on this side, now remember pi is just a number. So the radius is the variable, so we're going to bring down the 2. So we'll have 2 pi r, but we just took the derivative of r, so we're immediately going to follow it with dr dt. So no matter what variable it is, if it's a, dA dt, if it's r, it's dr dt, okay? But it's going to have a dt in the denominator, and that's giving us this respect to time. So this is the derivative for these concentric circles with respect to time. Now, they might say something like, let's see, so still dealing with the same problem. This is, if the area, or sorry, let me start again. If the radius is increasing at 1 foot per second, when the radius equals 4 feet, what is the rate the area is changing? Okay, so now they've actually given us the word problem here. So they're saying we've got our circles and the radius is increasing at 1 foot per second. So we're growing like this. The radius is increasing 1 foot per second. And then it asks us, what is the rate the area is changing at this one particular point? So the reason why this is called related rates is because there's more than one rate going in there, right? There's the radius increasing and there's the area changing. Okay? So what we should think about is where we're going to plug each thing. So the radius increasing, that's going to be in feet per second. So would that be dr dt? 1 foot per second. And r is given as 4. So they've actually given us dr dt, and they've given us r. Now with those two pieces of information, can we figure out what dA dt is? Okay, so we're just going to plug right in. So we're going to say dA dt, the change in the area, is going to be equal to 2 pi times the radius, which is 4, times the change in the radius, which is 1. So we end up with just 8 pi. And as this is a word problem, we won't leave it as 8 pi. So let's see, 8 times, where the heck is my pi? Pi. So we get dA dt is equal to 25.13. And then remember that we've got to put hello brain, we have to put a label on this. So area is going to be in square feet, right? If this was in regular feet, then area is in square feet. So square feet, but it's with respect to time, so it's per second. Okay, so that's our first related rate one. So we do the derivative with the implicit differentiation over here, and then we plug in the pieces that we are given. Now, these can be very challenging for people. It's one thing to follow along with me and do the problem with me. It's a completely different thing to sit down and do it on your own. So I'm going to put up here like a little kind of guideline, steps to follow. Now, some of you might be like, okay, I'm beyond that. I know how to do word problems, and that's fine. But for some of you, this might just help nail things down a little bit. Okay, so let's look at some guidelines here. So this says the first guideline would be to identify all quantities given. Okay, so as you read the problem, identify, there's going to be a lot of numbers in there, there's going to be a lot of variables in there. Identify everything that you're given, which means just write it down. Okay, write it down. Once it's written down, then it's easier to put into the function. Okay. The second thing to do after you've read the problem is to write an equation. So sometimes the equation will be given to you. Sometimes you actually have to write it yourself. Like this one, we had to read the problem and look at what we were interested in was area. So we wrote the area equation. Okay, so we took the time to do that. Then the third thing to do is to differentiate. So take the derivative, G8, implicitly. Okay, so take the derivative, but always, again, with respect to that third variable going on there. And then the fourth step is to plug in the quantities that we have noticed from above to solve. Okay. All right, so these are not problems that I make up on my own, because as we've got related rates, as we've got multiple things going on in the problem, it's harder for me to keep these things in mind, so we'll definitely go with the book. Okay, so this one says, find the rate and change of profit with respect to time and they tell us that the time is in days when 50 units have been sold. Sales have increased at 10 units per day, and the profit function is P equals 200 x minus 1/2 x squared. Okay, so we want to find the rate of change in profit, and luckily they gave us the profit function, but with respect to time. Okay, so there's that third variable. We've got x's and p's but we also have T going on there. Then it says when 50 units have been sold and that sales have been increasing at 10 units per day. So as it says here is to identify the quantities given. So the 50 units, that's our X, isn't it? So we're being told, and I'm going to leave this here so I can take the derivative underneath it. So we're going to write this over here. We're being told that X is equal to 50. And then it says sales have increased at 10 units per day. So again, X is units, day is going to be T for time. So what they've given us is also dx dt, units per time, okay? So dx dt, they're telling us, is 10. So that's what I mean by write down the quantities. I know that you can look in the problem and see the number 50 and 10, but what's important is to figure out what variable have they given us. They've given us x, but they've also given us dx dt. Now, we're interested in the rate of change in profit with respect to time, so we want to find dp dt. So now we've got our equation, we're ready to take the derivative. So remember, every single time we take the derivative of any term, we're going to follow it by that implicit dp dt or dx dt. So this first side will just be dp dt. Now the derivative of 200x is just 200, but immediately followed by dx dt. Minus, bring the 2 down so they'll cancel, so we just have x, but again immediately followed by dx dt. So there's the implicit differentiation with respect to time. Right? Now we have written over here the piece of information we were given. We can plug them into the equation, and then we can figure out our dp dt. So we'll say 200 times 10 minus 50 times 10, right? So we get 2,000 minus 500, so 1,500. Now remember, this is dp dt, so profit is in dollars, so dollars per, and our time was in days. So profit is changing $1,500 per day, not per days, per day. It looks like clay. Okay. Right? So when they're producing 50 units and increasing sales at 10 units per day, profit is increasing at $1,500 per day. That's a good thing. That's saying keep doing what you're doing. Okay, right now the rates, the related rates, they're all working together and we're getting a positive result. Okie dokie. Let's see another one then. Where's my eraser? My eraser in the book. All right, so this next one says the radius of a sphere is increasing at 3 inches per minute. Find the rate of change. Hold on, I lost myself. The rate of change in volume with respect to time when the radius is 9 inches. Okay, so another one using a shape here, okay? And again, this is another real world situation that pretty much all of us have done at one time or another. You just never actually did the math behind it, okay? But remember blowing up a balloon? That's what's going on here. Now, they're saying it's a sphere, so it's a perfectly round balloon, and I don't know if I've ever blown up a perfectly round balloon, but go with it. So when you blow up a balloon, you start blowing up the balloon, okay? The radius of that sphere, the radius of that balloon starts to increase. And as it increases, so does the volume, how much air is in there, right? Okay? And it's on a cycle of time, right, per second. So as you blow up the balloon, there are rates that are changing, and they're all related to each other, but with respect to time. So this is the equation for blowing up a balloon, okay? So again, we want to write down what we have here. So it says that the radius of this sphere is increasing at 3 inches per minute. So radius would be dr, but this is dr dt, right? Per minute is 3. They've also told us flat out that the radius equals 9. Now what we want to find is the rate of change in volume with respect to time. So we're actually looking for dv dt. And that's where we're headed. Okay, so if we want volume of a sphere, now that's not one that we should all have memorized, okay? I do, just because this is my job, but I wouldn't say everybody would need to know this one. But the volume of a sphere is 4/3 pi r cubed. Okay? Put that down in your notes now. Now you know the volume of a sphere, 4/3 pi r cubed. And that's what we're looking at here. So we're going to find the derivative here, but we're going to do it implicitly with respect to time. So that means the derivative of v is going to be dv dt equals, now remember, 4/3 pi, that's all the constant there. So we're going to bring down the 3 will cancel, so it'll give us 4 pi r squared. But now we've just done all that work. Don't forget that we have to follow it immediately by dr dt. Alrighty, so now we can plug in the pieces of information that we have, and we can hopefully find the change in volume. So we'll say 4 pi times radius, which was 9, so 9 squared, times the change in the radius, which was 3. Okay, so again, get out my trusty calculator, and this time we're doing 4 pi times 81 times 3, right? Okay, so dv dt, according to my calculator, is 3053.63. And now we're looking at volume. So remember, volume is going to be cubic units. So it's going to be cubic inches. So inches cubed per minute. Actually, this is the slowest blowing up of a balloon there ever was, but go with the flow. Okay? So we can tell how fast the volume is changing. Okay, one more of these guys, and then I think you'll be ready to practice some on your own. Okay, so this says a company increases production at a rate of 15 units per week. equals 211 minus 0.002x, and cost is C equals 30x plus 1,500,000. Find the rate of change. Find rate of change in profit when the weekly sales, the profit, I always forget that, profit with respect to time when weekly sales are X equals 1,600. Oh, okay, so they told us flat out that X is equal to 1,600, so that's nice. But then at the top here, they gave us this bit. The company is increasing production at a rate of 15 units per week. So that's going to be units, so that's going to be dx with respect to time, dt. Everybody agree? Is going to be 15. And we're looking for the rate of change in profit with respect to time. So we're looking for d capital P dt. But in this case, were we given the profit function? Okay. We weren't. So we got to do a little bit of manipulating before we ever get to the point where we can take a derivative. So we've got the demand function, but what do we have to do to the demand function to turn it into revenue? Okay, so we need to multiply through by an x. So we can say that our revenue function would be 211x minus 0.002x squared. Right, everybody agree with that one? Now, in order to find profit, we're going to take revenue minus cost. So that'll be our 211x minus 0.002x squared minus 30x minus 1,500,000. Okay, so 211 minus 30 would be 281, 9101, yeah. 281x minus 0.002x squared, and then that's going to be a, wait a minute, sorry, that was a plus originally. I got ahead of myself, so it's a minus when we come down here. Sorry about that. Got ahead of myself in the, there we go. Okay, so make sure your pluses and minuses are correct. Don't do what I did there. Hold on, I'm just having a bad day here. See, normally this is where I would love to have you guys out in the classroom to tell me, hey, you're screwing things up. So 211 minus 30 is not 281, but 181, yes? And just to be sure, I will use my calculator since life is not going well for me this morning. Minus 30, should have done that in the first place. Yes, 181, ah! Okay, so we're good. So this is P. Now we're ready to take the derivative. But after all that hard work, don't forget that this is implicit. So it's going to be dp dt equals the derivative here, which is just 181, immediately followed by dx dt. Minus, bring down the 2 here, so 0.004x dx dt. And then that guy just goes away, right? Okay, so now we have our derivative. We can plug in the different pieces that we have. So we have dp dt equals 181 times 15 minus 0.004 times x, which was 1600, times 15 again. And this is not one that I want to try and do in my head, especially since my addition skills are not great at the moment. So 181 times 15 minus 0.004 times 1600 times 15. So I got that dp dt is equal to 2,619. Okay, now remember that this is dp dt, so profit is in dollars, and this is per, what was our time in? Weeks. So when the company is producing 1,600 of whatever these units are, and they're increasing the rate at 15 units per week, they're seeing an increase in their profit of $2,619 per week. So again, it tells you that, yeah, that increase in production is helping them out. All right, look good? Okay, so remember the guidelines here when you're doing this, that the first step is always to see what you're given, okay, see what you're given, and then write an equation. If the equation isn't given to you, then write an equation, because sometimes looking at what you're given will help you decide what variables you're using and what equation you're looking at, okay? So take that time at the beginning to set it up properly, and then taking the derivative is easier. Okay? And then the final step is just to plug in, and we can do that. Okie dokie, so that's related rates. So I want you to practice with that. It is not good enough to just follow along with this lecture, I promise you. You absolutely must practice this on your own, okay? Otherwise you will not be able to do it, I guarantee it. Okay, so go and practice. Okie dokie, have a good day.